Good morning, everyone. Welcome to the last lecture of atomic structure. Myself, Suman Singh. So, in the last class, we have discussed about the quantum number, right? So, in this class, we will discuss about nodes and the electronic configuration. Okay, type of nodes and electronic configuration. So, when we talk about the node or node is what? Node is a three-dimensional space around the nucleus where the probability of finding an electron is minimum or zero. You can say that node is what? Node is that plane where the probability of finding an electron is almost zero. Okay, where the probability of finding an electron is zero. So now as you can see here in this diagram, node is what? This plane is called node. As you see this one, the black color, right? This one is called the node where the probability of finding electron is zero, almost zero. So when we talk about the nodes are of two types. One is radial nodes, another one is angular nodes. So radial node is what? Radial node is a spherical region around the nucleus where the probability of finding an electron is zero. Okay, means psi square is zero. Okay, angular radial nodes. Now, when we talk about the angular nodes, or at that time, what we can say, similarly, the nodal plane or angular plane has a zero probability of finding an electron. Okay, so when we talk about the calculation, how to calculate the nodes, so always remember that radial nodes will be equal to n minus 1 minus l. Okay, or sorry, n minus l minus 1. Okay, so here n is what, right? In the last class we have learned, right? This n is what? It is a principal quantum number, and this l is what? This is l is azimuthal quantum number, and this is 1. So to find out the radial nodes, will use this formula n minus l minus 1. Okay, as you can see here, the number of radial nodes is n minus l minus 1. Now, and always remember that angular node is always equal to l. Okay, angular node is always equal to l, and whereas radial nodes is n minus l minus 1. Okay, so now one example is given here. As you can see, if we have to find out the nodes for 3p orbital. So if we know, when we talk about the 3p, means what we can say, n is our what? 3, right? N is 3, and l will be what? When l will be, in the previous class we have learned, right, this one. If our n is 3, then l will have 3, l will have 0 1 or 2, right? 3p 3s 3p or 3d, or we can say that when l will be 1, right? Because as you can see here, when we talk about the 3p orbital, number of nodes is what? 3 minus 1 minus 1. Okay, where l is equal to 1. If n is equal to 3, then l is equal to 1. Okay, after that angular node is what? It is equal to 1. You can see here. Okay, and the total number of nodes will be 2, right? So in this way we can find out the number of nodes when it is given, when any orbital is given, and from that orbital, by using this formula, we can find out the number of nodes. Okay, now again, when we talk about the orbitals, now shape of the orbitals, we know that the s orbital is spherical in shape. Okay, the s orbital is spherical in shape. As you can see here, this is the structure of s orbital. Okay, this is what? It is spherical in shape. So what we can say, s orbital, when we talk about the s orbital, orbital can accommodate electrons with l is equal to 0. Okay, this, when we talk about this s orbital, this orbital can accommodate electron with L is equal to 0, and these orbital are present in every orbit starting from the first orbit. What it means to say that in every orbit, if you talk about if you talk about n is equal to 3 or n is equal to 2 or n is equal to 4, anything, first of all it will be spherical. First of all, this L is this one s orbital will come first, after that only p orbital, after that d orbital. Okay, so in every time you will get the s orbital. As you can see here, s orbital can accommodate electron with L is equal to 0, and these orbital are present in every orbit, means in all the orbit you will get this s orbital. Okay, in all the orbit you will get s orbital. Okay, I hope you know the difference between orbit and orbital, right? In the previous class also we have discussed, as it is written here, you can see in the notes. Okay, so in every notes, in every orbital there will be a in every orbit there will be an s orbital. Okay, and the shape of orbital is like this, you can see here. Now again, what we can say, orbital in which n is equal to 1 and L is equal to 0 are present in 1s. All the electrons in when we talk about the orbitals, in an orbitals, electrons which whose value is n is equal to 1 and L is equal to 0, then it is obvious that it will be in 1s orbit. Okay, 1s orbital. And all s orbital are spherical in shape, as you have seen in the figure, is spherical in shape, and the size of the sphere increases with n value. And as I have already told you, right, if we are talking about n is equal to 1, then it will be, suppose this is a nucleus, n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, like this. So as we go away from the nucleus, the size of the s orbital increases. Okay, so as you can see, the s orbital are spherically symmetrical because the probability of finding an electron around the nucleus in is same in all the direction. Means why this mm, s orbital is spherical in shape, because the in s orbital the probability of finding an electron is everywhere. Okay, suppose this is a nucleus and this is an s orbital. So as s orbital is spherical in shape, suppose this is all s orbital, means the probability of finding an electron in s orbital is everywhere. Okay, so this was about the s orbital. When we talk about the p orbital are dumbbell in shape. Okay, as I have already told you in the last class, this is dumbbell like. Okay, like this, dumbbell shape. Okay, and what we can say, p sub level or sub level begin from the second orbit. For p subcell, L will be 1, and indicate that each p subcell contains 3 m, as we have calculated, right? For L is equal to 1, m value will be 3 values, right? For L is equal to 1, the value of m will be 3, right? 1 minus 1 0 and plus 1, as I have already discussed this in the last class. So for n is equal for L is equal to 1, m value will be minus 1, 0 and plus 1. If L is equal to 2, then it will be minus 2, 1, minus 1, 0 and 1 and 2, like this, right? 5 values. So in the same way, as you can see, for p orbital the value of L is 1, and it indicates that p sub level contain 3 orbital with m value of minus 1, plus and 0. Okay, and these are generated at px, py and pz. This minus 1 is suppose px, this one is py, and suppose this is pz. In this way it has been given the name. And when we talk about the shape, its shape is like this. As you can see, its shape is like this here, and this is along x-axis. When it is along x-axis, it is px. When it is along y-axis, as you can see, it will be py. When it is along z-axis, it is pz. As you can see here, how you can draw, it easily. It is, you can draw like this, like this. Okay, so if it is along x-axis, it will be pxy. If it is along y-axis, it will be pxy, 2py, and if it is z-axis, it will be to pz, okay, as you can see here. And one more thing you see here, it is written p, right, 2, right, 2px, 2py and 2pz, because in the first orbit, as you have an orbital, in the first orbital you can see that only 2s is there, right. Sorry, 1s is there. In the first orbit you will not get p. In the first orbit only s, after that 2s and 2p, right, like this we have learned this, right. So, and this was the so what we can say, in px orbital, electron density is concentrated along the x-axis, and in p orbital have a dumbbell shape, as a you can see it is like this, right, dumbbell, like a dumbbell, right. And each p orbital has a two lobes separated by one nodal plane. You can see when we discuss about the nodal plane, I can show you where will be the nodal plane. So suppose like this, you can see here, suppose this is our p orbital, okay, along the x-axis, okay. Suppose this is the axis here, along the x-axis. So what will be the nodal plane? So when nodal plane will be this, okay, nodal plane will be this, which is dividing these two. This will be the nodal plane, okay. So as you can see here, it has it has two lobes, and the probability it has two lobes and one nodal plane, okay. And the probability of finding an electron is here in this area, okay, not in this area. The probability of finding, since the probability of finding electron is in this area, okay. And it has one nodal plane, as you can see here, okay, because this one is just dividing this from the middle, right, along the axis. So as you can say, each p orbital has a two lobes separated by one nodal plane, as I have shown you, and the probability density function is 0 on the plane, and the two lobes touch each other, okay. And now this nodal plane for px, py and pz is, when it is px, as I can show you like this, when it is along px, when our this one, I will show you from this table, as you can see here, when it is along px, as you can see px, right, this is along, this is our 2px. When it is px, the nodal plane will be along yz, okay, yz. And after that, when it is to py, the nodal plane will be zx, okay, and when it is to pz, at that time the nodal plane will be xy, okay, along the xy direction. So this diagram you can also see in your book, it will be given in your book. Now next, what we can say, the three orbital present in a given p subshell will have a same energy, same size, okay, same shape, size and energy, but difference in orientation. Now, as I have already told you, the orientation will be different, but the shape, size will be, and the energy will be same, okay. So this was about the p orbital. Now we will see about d orbital. So when we talk about the d orbital begins from the third orbit, okay, n is equal to 3, as we have seen here, the p orbital start from the second orbit, n is equal to 2, okay. So it will start from 3 third orbit, n is equal to 3, and since since n is equal to 3, then L will be what, 2, right. And if L is 2, then it will have a 5 values, as you can see here. And these 5 values are what, dxy, dyz, dzx, after that dx square, y square and dz square, okay. So how we can draw this? We can draw like this, as we can see here, it has been drawn here. How it has been drawn? When it is dxy, when it is dxy, it is like this, it is along dxy, this is dzx, okay. After that dyz, after that dx square, y square and dz square. Here when we talk about our dz square, you can see here it is like this, okay. This is like this, one is like this, okay. One lobe is like this along the axis, okay, along the z axis. One lobe is like this, suppose this is the z axis. Along the z axis, that is, this lobe is here and this lobe, and one is in the just like this, spherical, okay, in the, which is circling this one, as you can see here. So this is the structure of the d orbital. Okay, so I hope you have understood about this say shape and size of the shape of the sp and d orbital. Okay, so now we will see the electronic configuration. Okay, electronic configuration of a multi-electron system. When we talk about the single electronic system, at that time the electronic configuration will be like this, as you can see here. 1s will be greater than 2s, but 2s and 2p will be similar. Again 2p, from 2s and 2p, this 3s and 3p will be bigger, but this 3s, 3p and 3d will be same. After that, this 3 will be greater than with 4s, and 4p will be greater than will have a more energy than 3p or 3d, but it will 4s and 4p will be have a similar energy. 4d also have a similar energy, and 4f also have similar energy. So this is for a single electron system, but for multi electron system, when we will see, the scenario will be different. So in the multi-electron system, what we can say, the distribution and arrangement of electron in the main shell or subshell or and orbitals of an atom is called the electronic configuration of the element. Okay, so what is this electronic configuration? Electronic configuration is nothing but an arrangement of electron, okay, in the main cell, or we can say that in the subshell, or in the or we can say that orbital of an atom. Okay, so regarding the electronic configuration, so many two or we will see regarding this electronic configuration. One, the major, what we can say, the major thing which we consider is the above principle. Okay, so this is above principle. What is this above principle? What does he says? So he says that any fully filled suborbital having lesser n plus l value. Okay, what he says, any fully filled s orbital having lesser n plus l value, okay, will have a lesser energy level, and n plus l value is same then the suborbital having n less n will have a less energy. Okay, what he wants to say that, to for any fully filled suborbital, we will have having n plus 1 value, n plus l value, uh, we will see the n plus l value. Those, if n first of all, if we are asked that either 2s or either 4s or 3d, which one will come first, so at that time we will see the n plus l value. If the n plus l value is same, then we will see the n value. If n is less, then we will give them the first place. After that, we will put the one whose n value is more. So I will give you example, you can see here. So now what he says, he says that he says, in a ground state of an atom, the orbital are filled in order of in their increasing energy. Okay, in order of their increasing energy. In other words, electron first occupy the lower energy orbital available to them, and enter into the higher energy orbital only after the lower energy orbital are filled. Okay, so some of the example are given, as you can see here. What he says, n plus 1 rule, above principle is based on this n plus l rule. Okay, so as the n plus l value increases, the energy of the orbital also increases. If the n plus l value will be more, then the energy of that orbital will also be more. Okay, and the orbital with lowest n plus l value is filled first, means those orbital in which whose n plus l value is less, they will be filled first. Okay, when we fill the electronic and when we will do the electronic configuration, at that time we will see the one which has a lesser value of n plus l, that orbital will be filled first. Okay, now again, when two or more orbital have a same n plus l value, the one with the lowest n value, whose n value will be lowest, will be filled first, or we can say that will be preferred in filling. So now we will take one example. When we talk about this 3d and 4s orbital, so n plus l value of this 3d is what, 3 plus 2, that is 5. Okay, and when we talk about the this 4s orbital, it you can see n plus L value is 4. Okay, but since this 4s has a lowest n plus L value, okay, it is filled first before filling the it is filled first before filling take place in 3D. Means what, we used to fill first 4s, after that only we filled 3D, because we can see the n plus L value of 4s is less, right, it is 4, but when we will see the n plus L value of this 3D, it is more, it is 5, right. So we will fill first 4s, after that we will fill 3D. Okay, now next, if you are considering the 3D, 4p and 5s, okay, so as we know, L plus L, n plus L value of 3D is what, 5. Okay, and the n plus L value of 4p is 5, and n plus L value of 5s is also 5. So these three values are same. Okay, so when these three values are same, then what they have, what above has told, that if the n plus L value is same, we will give a preference to lowest number of n. So as the lowest number is this, right, 3D, after this n value, and the n value of n, the value of n in 3D is less, after that 4v 4p, after that 5s, right. So when the filling will start, at that time we will fill first 3D, after that 4p, after that 5s, right. As you can see, since these three values are same, the n value is lower to 3D orbital, and the electron prefer to enter first in 3D, then in 4p, then after 5p. Okay, so since why it is happening like this, because the n plus L value is same. So when the n plus L value will be same, at that time we will see the value of n, whose n value, if the value of n is small, then we will fill first that orbital will be filled first, and after that the next orbital. Okay, now the order of increasing the atomic orbital, when we talk about the order will be like this: 1s, 2s, 2p, 3s, 3p, 3p, after that not 3D, as I have already given you the example. After 3D it will be 4s, after that 3D, again 4p, 5s, 4D, 5p, 6s, 4f, like this the series will go on. Okay, and now this sequence in which the electron occupy the various orbital can be easily remembered with the help of this Molar diagram. As you can see, this diagram, it is given, it is like this. Okay, first of all, one electron will enter the 1s, after that 2s, after that 2p, then 3s, then 3p, 4s, after that this 3d, 4p, 5s, after that 4d, 5p, again 6s, after that again it is 4f, 5d, 6p, 7s, again 5f, 6d and 7p, like this. And this one, if you want to write, you can write very easily. Then you can see here 1s, 2s, 3s, 4s, 5s, 6s, 7s, right. It is just in the sequence. After that 2p, 3p, 4p, 5p, 6p and 7p, after that 3d, 4d, 5d, 6d, after that 4f and 5f, right. Why? Because in the first orbit only s orbital is there, in the second s and p both are there, in the third spd is there, in the 4 spdf is there, in the 5 spdf, in the 6 spdf and 7 spdf. So in this way also you can easily remember how to, which one will be filled first, and after that next which one will come. Okay, now after that, after the above principle, Pauling exclusive principle, we will see what does he says. He says that no two electron in an atom can have a same set of value of all four quantum number. Means what, when we will see any element or any electron, suppose this one is electron and this one is also an electron, this electron and this electron, both of them will not have this all four quantum number. If three quantum numbers are coming same, then it will be different in spin quantum number. If I think you are understanding that, because no two electron means no two electron will have all four set of quantum number will be same. It is not possible that all the four quantum number, just like azimuthal, principal, magnetic or spin, if principal, azimuthal, and magnetic quantum number is same, then it spin quantum number will be different. Okay, so Pauli exclusive principle, what he says, no two electron in an atom have a same set of all four quantum number. This means that the two electron in an orbit may have the same value of n, may have the same value of n, if the same value of m, but they will be different in the spin quantum number, right? So he says that if two electron in an atom has the same value of n, l, and m, but the spin quantum number will be different. Okay, so this was about the Pauli exclusive principle. Now next is Hund's rule. Okay, Hund's rule of maximum multiplicity. What does he says? He says that while filling an electron in any suborbit, pairing of electrons would not occur until and unless all the orbital are half filled. What he says that pairing of electron will while filling the electron in any suborbit, pairing of electron will not occur until the and unless all the orbital are half filled. Means what? I will give you one example is given here. I think yes, you can see here. Yes, here you can see in nitrogen it is you can see the filling is like this: 1s2, 2s2, and 2p3, right? So when we talk about the s is like this, p is like this. Okay, 1s, wait, let me draw it again. This one is suppose our 1s, this one is 2s, and this one is 2p. So according to Hund's rule, what does he says that when the filling of orbital when we fill the electrons in a suborbit, at that time pairing of electrons would be pairing of electrons will not occur. So what does he says? When we are suppose we have to means fill this one. Okay, so for n is equal to 7 for nitrogen. So suppose this is our 1s, this is our 2s, and this is our 2p. So according to Hund's rule, suppose this is 1s, this one is 2s, and this one is 2p. So according to Hund's rule, first this one will filled, after that this, then after that this one, it will not like this, it will be not we can't write like this. Okay, we can't write like this, it should be like this, it should be like this. First of all we have to fill half, after that we will fill the full. Okay, so it will be like this, and like this. Okay, it is not like this, we can't fill like this. According to Hund's rule, we can't fill like this. Okay, so what he says, while filling in electrons in any suborbit, pairing of electrons would not occur until and unless the all the orbitals are half filled. Okay, as you can see, all the orbitals are half filled. First we will fill half, after it we will fill the double, right? So this was the simple example. Okay, I hope you have understood this. Now next you can see some of the electronic configuration is given here. Okay, 1 to 30 electronic configuration about 1 to 30 is given here. So you can see here, and the exception I have already told you, and yes, the exception I have already told you. Now next is stability of atom. So when we talk about the stability of atom, extra stability is associated with an atom in which the degenerate orbital are half filled or completely filled. Okay, which atoms are when we talk about the stability of atoms, which atom will be more stable? I will give you one example. If there is one atom whose um, last orbital, okay, last orbital is like this, half filled. Okay, or the last orbital is like this, fully filled. Okay, last orbital is, outermost orbital is fully filled, this one is half filled and this one is fully filled, and one is like this, one is like this. Okay, and another one is suppose like this. Okay, so when we talk about the stability, this one half filled will be more stable than this. Okay, or we can say that this fully filled is more stable than this. So this one fully filled and half filled will be more stable than this. Okay, I hope you are understanding this. So this one here, extra stability is associated with an atom in which the degenerate orbital are half filled or completely filled. If the orbital are half filled, or if it is completely filled, that will be more stable than the one which is not half filled or not fully filled. Okay, now why it is happening? Due to the symmetrical distribution of electron. Okay, and the next is exchange of energy. Greater the exchange of energy, greater will be the stability. Okay, now again what we can say, the presence of half filled and completely filled degenerate orbital gives a greater stability to atom. Means if the atom is a half filled orbital, if the atom has a half filled orbital or fully filled orbitals, at that time they will be more stable. Okay, now as example you can see it is given in the in it is for this reason that the electronic configuration of chromium and copper, okay, are represented in like this. Okay, why it is represented like this? Because you can see this one 3d5 is more stable than if we want to as you can see here 3d5 is there, right? So 3d 3 4 5, yes, this is suppose 3d. So when we are filling for this chromium, at that time if we will fill like this 1 2 3 4 and 5, this one will be more stable. If we were what we are doing in place of this, if we are filling like this one we are not filling, we are just filling, giving here double. Okay, so at that time if we are giving here, then this is not more stable. Okay, more stable will be this one, is more stable will be this one. Okay, when we are giving here. Okay, one here, one here, and one here, and one here. Okay, so that is why you can see here 3d5 it is written, right? So 3d5 is filled like this. Okay, in the same way as you can see here 4s1 and 4 3d10. So in place of 3d10, why it is written 4s1? If we are 4s1 is, you can see here one electron only, right? And for 3d, since 3d is 3d10, 1 2 3 1 2 3 4 5. So 1 2 3 4 5, after that 6 7 8 9. If we are feeling like this, okay, if we are feeling like this, then it will be and then it is not so stable. Okay, but when we are feeling like this, when it is we are giving him one electron, and if we are giving him two electrons here, now it is completely filled, this 3d is completely filled, and 4s is half filled, so both are stable, right? As I have told you, 3d and 4s are more stable. So as you can take the example of this helium, so if you take the example of helium, it is what, 1s2, right? So 1s2 it is like this, completely filled, that is why it is more stable. So what we can take that the way, what we can say, the stability, when we talk about the stability, half filled and fully filled are more stable than the uh, half filled and fully filled are more stable. The atom which is have a half filled or fully filled orbitals, they will be more stable. Okay, so this was all about your atomic structure, and this is electronic configuration. As you can see, if you have any doubt, you can send me a message in. Okay, so in the next lecture we will start with the periodicity. Okay, till that, thank you.